And we now proceed to the last talk of this morning's session. James Scott, Regularization with Variance-mean.
Thanks very much. I want to extend a thanks to the organizers of the conference, especially Becca, who I can see has been running around like crazy trying to sort all the problems that arise. And also thank the staff of the Washington Duke. This has been really top-notch, and I've enjoyed myself a lot. I'm James Scott. I'm a Bayesian statistician from UT Austin, describing joint work today with Nick Polson of the University of Chicago. Let me jump straight to the punchline. So on the left here, I have a whole bunch of statistical models. Let me call them likelihoods since I'm a Bayesian. And on the right-hand side, I have a whole bunch of priors or penalty functions. The result that I'm going to describe here today is an algorithm that works for arbitrary combinations of what's on the left and what's on the right. Moreover, it does so with no matrix inversions, no numerical derivatives, and it gives you fully parallelizable, almost embarrassingly so, although not quite, block updates. So it's not a coordinate descent algorithm. Okay, so pick your model on the left with your penalty or prior on the right, and this approach will work, and some others too. To those of you that sort of do work in this area, I'll describe in 20 seconds how we get there. If you're familiar with the normal scale mixture trick that gets you everything on the right, well, we do a similar trick with the likelihood. It's not quite the same trick, and we get all the likelihoods on the left. You put the scale mixture trick on the left with the scale mixture trick on the right, you get a really, really easy EM that's amenable to being solved with no matrix inversions. So let me go ahead and get there. Okay, and one thing that you might be thinking is that all of those problems that I mentioned can all be solved, especially the ones on the left, with a lasso-type model or an L1 constraint. Well, maybe this is just because I'm a Bayesian, but I'm allergic to L1 constraints. And it's because I've seen too many examples like this. So here is just a really, really simple set of simulated data where I'm taking a probit model. So I'm generating some latent z's from a homoscedastic regression model. X beta is the mean. And I'm going to threshold those z's at 0 to get me some binary observations, so just a textbook probit model. And my betas are this R-spike signal. So that's a famous class of signals that got trotted out a lot in the Stein estimation literature in the 70s and 80s. And it's 5 copies of the square root of 5 and 20 copies of zeros. That's the signal. Okay? And on the bottom here, you can just see, I'm estimating using 3 different procedures here, 2 variations in the lasso, one where I choose the regularization parameter using the universal threshold ideas, the Candies and Tao, Donho and Johnston square root of 2 log p idea, and one where I choose that regularization parameter by cross-validation. That's how well I do versus the MLE. And then I do something that's a little, I'm not going to tell you what the 4th thing is. It's another estimator called the horseshoe estimator, and you just do drastically better. Okay, and so, an example after example after example, Bayesians who work on this see L1 constraints getting hammered. And so, we don't like the L1 constraints. And let me just show you a quick example. This is a little movie of data drawn from exactly the same model that Larry was just showing you in that talk, a whole bunch of IID normal means. In this case, it's the homoscedastic model. So you can see the 10 signals plus 1 noise observation out there in the tail. And I'm just going to show you what happens under the double exponential model, which is the model that leads you to the lasso or L1 constraint as you get more and more noise. So there's all the noise. And what you're seeing is the posterior mean, not the posterior mode, but it's really the same thing. As you get more and more and more noise, you start missing drastically more in the tails. And that's just sort of a known property of the L1 constraint, of the lasso estimator. And again, what would the mode do here? The mode would take those rounded edges and just square them off at 0. But you're still going to miss in the tails by a proportionally larger amount the more and more and more noise you get. And this is sort of a depressing problem in stats. There seems to be this complete separation of priors and penalty functions into the computationally nice class and the statistically nice class. And you look at the stuff on the top and you say those are nice convex constraint sets, nice convex penalties, but they don't look like sparse penalties, that's for sure. There's a lot of mathematics behind this in a lot of these papers going all the way back to the 70s. But it's very common sense to just look at the constraint set on the bottom there and say, well, if I want something sparse, I want something that concentrates near the major axes of RP. And that's what the statistically nice penalty functions like, as opposed to the computationally nice convex penalties on top. Okay, so what's our contribution here? I want to stay away from L1 constraints. I want to do something that looks more like the constraints on the bottom there. But now we're outside the class of things that are easy to solve computationally. So that's our contribution, an algorithm that works for a very wide class of non-concave penalized likelihood problems where the likelihood itself is non-Gaussian. Okay, so let me give you a teaser example of how this works. So this is the objective function that corresponds to a regularized logistic regression model with a bridge penalty. Okay, so I've just put what is the tau out there. That tau, you can think of that as being the regularization parameter that often gets put. Oh, I don't have a pen. Where'd that laser pointer go?
It's there, but the battery fell out.
No problem. Okay. Okay. Well, you see the tau inside the absolute value of the betas. Sometimes people write that outside. I'm just writing that inside. And the SJs can be your adaptive lasso type factors if you want them. Okay. And when alpha is less than 1, this is a non-convex problem. Ouch. Right. Okay. So our results show that to solve this problem, I don't have to do coordinate descent. I just need to iterate 3 steps. What's the top? The top looks a lot like a generalized ridge least squares type solution. And there's some unfamiliar factors in there. I'll show you in the rest of the talk where we get those factors from and why it looks the way it looks as opposed to an ordinary least squares or an ordinary ridge regression problem. And then the bottom 2 things are just these little, the omega I inverses. Those go along the diagonal of the capital omega in the top line, and the little lambda j inverses. Those go along the diagonal of the capital lambda in the top line, and that's it. I get the solution to the logit bridge penalty, no pain with the non-convex problem. Okay. And remember I told you no matrix inverses at the beginning. You may think, you look at that line and you think I'm lying. I'll show you how to get away from actually inverting that matrix. So how would you, I think there's so many applications to name of these kinds of methodologies. Here's one that we're motivated by, where we really need scalability. So we have a data set with some collaborators of mine at St. David's Hospital in Austin, Texas, where they have about 112 million patient records. If there's one thing insurance companies are very good at, it's keeping billing records. And they have records on what are called ICD-9 codes. They're basically billing codes. So here's an example of a billing code that appears when you show up in a hospital with a heart attack or something. You get a myocardial infarction of the other inferior wall, and that gets coded as 410.4. So that's a 1 in the 410.4 column of our data matrix with 112 million rows. We also have data on prescriptions. One cute fact about our medical system that I never realized is that whenever you go in to a hospital, bazillions of shadow prescriptions get created. So we have I remember looking at one particular record that was a 3-week visit to the hospital for a subarachnoid hemorrhage, a burst blood vessel in the brain, and there were 7,000 shadow prescriptions. Now, only a tiny fraction of these ever actually got filled, but they were generated automatically by the system. We've got that data too. We also have covariance. So one thing that we're interested in is building what I might call a tree of graphs here. The graphs at the bottom at the bottom nodes of the tree are a disease network, telling you what's the conditional independent structure between this and maybe diabetes and strokes or something like that. All the different ICD-9 codes. Thank you very much. Great, thanks. Well, true to form, I can't get it to work. So there we go. Okay. So this is not our disease network. This is a really popular topic. This is just from an article in PNAS about 4 years ago. But we're imagining splitting the tree on covariance, like demographics and geography, and each baseline node in the tree, terminal node, looks like one of these, the disease networks, estimated by penalized logistic regression. Not O1, nothing convex. All right. So here's the big picture that I kind of mentioned in 20 seconds at the beginning. We're going to use the theory of variance-mean mixtures to kind of get this very, very broad class of likelihoods and penalty functions, solve them all with a really simple variant on the EM algorithm. Things like logistic regression are pretty simple by modern Bayesian standards, but when you get a data set of 112 million, often they're the only tractable approach, and even then they're still pretty intractable without some cleverness. So, this class of objective functions that submits to this tactic of representing them as variance-mean mixtures of normals is actually surprisingly broad. It includes something, for example, like this, which you might recognize as a logistic normal topic model. You may be used to thinking of topic model as something like latent Dirichlet allocation, where the topic parameters have a Dirichlet distribution. Well, here, the topic parameters, instead of having a Dirichlet distribution, they have what's called a logistic normal distribution. Instead of chopping up the increments of a gamma and normalizing them, like for a Dirichlet, you chop up the increments of a log normal distribution, and you normalize them. That's all that's different. And we're able to solve this problem exactly, get an exact map estimate, no variational approximation, using the trick I'm going to show you today. There's too much work on topics like this to name, so I've just listed a lot of the sort of relevant literature and the three kinds of broad areas that we're unifying here. Obviously, there's been a ton of work on representing penalty functions with scale mixtures of normals. There's been quite a lot of work on algorithms for regularized regression, mostly from the classical community, but also some from the Bayesian community. Steve Scott, in particular, has a really nice paper in the most recent edition of Bayesian analysis that shows how to do basically the trick we're doing today for the special case of support vector machines, which is a cool trick. And then today, maybe the new part, I say, there's 1923 up here, so not so new, but bringing these ideas into regularized regression, the new part today is distributional theory based on variance-mean mixtures. So a lot of folks here are familiar with the standard scale mixture trick, where if I have some density P of Z, I want to make it analytically nice to deal with. Instead of working directly with P of Z, while I augment the space with this variance, I get a conditionally normal representation, so that phi there is the normal density function with mean 0 and variance v, and I mix over the variance v with respect to some prime. Okay, so probably used to seeing that trick in a lot of different cases, most often in the regularized regression setting, where, for example, if I have my regression coefficients being conditionally normal, the global variance, think of that as the regularization parameter, and a whole bunch of local variance is idiosyncratic to the betas. Well, if I put different mixing distributions on those local variances, the lambda I squareds, I can get different penalty functions that you've heard of: lasso, bridge, horseshoe, normal gamma. And all the action is in choosing what that prior is right there. Okay, well, we just changed that trick up a little bit. And there's actually two ways, at least two ways, that you can generalize this framework. I won't talk about the Levy representation today. I'll just say that it's a really, really useful generalization for getting group versions of all of these common penalties, like non-convex versions of the group lasso, group bridge, group SCAD penalties, that kind of stuff. And I won't go into details on that. I will talk about mean variance mixtures. Okay, so this is really simple. If you think of the scale mixture trick as like taking Brownian motion, observing the increments of Brownian motion with a random stopwatch, maybe a gamma distributed stopwatch or an exponential distributed stopwatch. All this is taking Brownian motion with the drift and having random increments on the stopwatch. And that's your distribution right there. So there's a mean term, there's a drift term kappa, and so you just notice that the only difference up here is that the variance that I'm mixing over enters into the mean parameter of this Gaussian random variable. And that's it. Okay? So let me stipulate for now that this can be done. All right, and I'll show you in a couple of slides for what kinds of problems it can be done and precisely how we get there. So, if you work on problems like this, you could think of, well, maybe I've got a t likelihood with a lasso penalty. And it's probably not going to surprise you that if I've got a t likelihood and a lasso penalty, both of those are scale mixtures of normals, that I can create a pretty simple EM that will get me to the mode. And that's all I'm doing. I'm going to write that, let's imagine that I've got except I'm going to do it for more than just t distributions. So here's my objective function. It's a general, here's the likelihood piece, a general function of y and the linear predictor xi transpose beta. Here's my penalty function. There's my scale of regularization tau. And I'm just going to exponentiate that whole thing, e to the minus q of beta, and get, I think of it as a posterior distribution. You don't have to. You can think of it as a pseudo-posterior. There's nothing intrinsically Bayesian about this way of proceeding. It's just, think of it, if you want to, as artifice for getting the map. So I'm going to factorize this into P of z of vector z, which are either going to be residuals for regression or sign-flipped linear predictors where yi is going to be +1 for a success or -1 for a failure here for a classification problem. So, the posterior here is going to factorize into the likelihood and the prior, the conditional likelihood and the conditional prior. Right? Okay. So now suppose that I can do that trick that I just showed you with both the likelihood and the prior. So I can represent the likelihood as a variance-mean mixture of normals and the prior as a variance-mean mixture of normals. And they all have that exchangeable structure like that. So everything breaks down into a product of conditional likelihoods over zi's and conditional priors over beta j's. And each of them have that structure right there as a mean variance mixture of normals. Well, it's not going to take a lot to convince you that that's really amenable to an EM. Everything's going to be conditionally normal, and I'm going to get nice closed form updates for those latent variances, omega I and lambda j. Okay. What's nice is that because of the properties, because of well-known properties of the normal distributions, when I'm doing this EM, I'll skip this slide here, I never ever have to actually know anything about the distributional properties of the omega i's or the lambda j's. All I need to know is the derivatives of the log likelihood g, I'm sorry, the penalty function g and the log likelihood f. Okay, and since those are pre-specified, I'm outside of the normal situation in Bayesian inference where I have to know what the distributional properties of those local variances are in order to do inferences. So this is very unlike a traditional MCMC approach. And that theorem right there is completely general for anything in the class. So let me not go into too many details on the E and EM step. Let me just now jump to, for what models is this useful? So again, it's no mean trick to do this for a t-distribution likelihood, which we know just natively is a skill mixture of normals. It turns out that a whole lot of common models can be written as mean variance mixtures of normals, and this trick works for them. So for example, check loss, which gets you quantile regression. Turns out that this guy right here, that as a log likelihood, a negative log likelihood right there, is a mean variance mixture of normals. It's hard to believe. The support vector machine likelihood is a mean variance mixtures of normals, and so is the logit. And the logit actually does a lot of heavy lifting for a lot of different models, because there's a ton of models that can be written in terms of logit type likelihoods. Okay. Let me get this off. Okay. So how do we get there? Well, it's you know, in many ways this is just a cute calculus trick. If I take a mean variance mixture of normals with respect to something called a generalized inverse Gaussian mixing distribution. Okay, so many of you will be familiar with the inverse Gaussian from a hitting time Brownian motion style result. Well, this is just a generalization of that distribution. And this is just this is an integral equation. It's just true. And it turns out that if I mix over that mixing distribution right there, I get that marginal distribution. And you can see right away I'm going to get something like a check loss in quantile regression as a mean variance mixture of normals out of that. Here is where I get logits from. And more generally, kind of powered up versions in the numerator and the denominator of a logit likelihood function. And what's the mixing distribution? It's called a Poya distribution. Right? And there's improper versions where this thing right here doesn't actually correspond to a density. It just corresponds to some function that's the limiting version of one of these generalized inverse Gaussian or Poya densities. And you get logit, you get the check loss, you get quantile regression, you get support vector machines from all of these improper limiting cases. To say about this, let me give you the example of the logit, since I sort of put that as the teaser example up front. The Poya distribution is sort of an esoteric one. It turns out to be an infinite convolution of exponentials. So here's the density function, and it's equal in distribution to essentially a weighted decaying sum of exponentially distributed random variables. And here's just some not very informative expressions for the terms in this infinite sum up here. But it's perfectly tractable. And it turns out if you have a Poya mixing distribution for that variance term in the mean variance mixture of normals, you get a Z distribution marginal, which is a class of distributions first studied by Fisher in 1923. So they've been around a while. And this looks obviously a lot like logits with particular choices of alpha, kappa, etc. Okay? And you choose your alpha, you choose your kappa, and the theorem that I showed you for the EM is going to give you closed form expressions for those updates in those latent variance terms. About 5 minutes? Is that right? Okay. This can also work for the multinomial logit. So we use a little trick that Holmes and Held used in their 2006 Bayesian analysis paper to essentially write the multinomial logit model as a conditional series of univariate logit models. I won't bore you with the algebra on this one, but I will, point out that. Let me go through to this step right here. Okay. So this is the part where I promised you that you wouldn't have to invert a matrix in order to implement this method. Inside this EM, I've got a whole bunch of univariate updates for n latent variances associated with the likelihood and p latent variances associated with the penalty. Those are really, really simple. Each of those is just maybe one or two multiplications or additions. And then the real bottleneck here is to solve this linear system. Once I concatenate all of those latent variances from the likelihood into this diagonal matrix omega here, and all of those latent variances from the prior into that diagonal matrix there, now I have to solve for beta. Well, it turns out that you don't actually have to solve it. Because this is an EM, it's enough, rather than to solve this system, simply to approximately solve it. And as long as I'm improving the observed data objective function at every iteration, that's going to be enough. So instead of solving the system and paying this huge price of inverting a matrix or doing a full QR decomposition or something, let me just take 5 or 6 steps of a conjugate gradient algorithm, for example, or some clever method for solving this linear system. Okay, so instead of solving it, don't solve it. Instead, do something like this conjugate gradient. And for those that don't know the conjugate gradient too well, I find that in stats audiences, not a lot of folks tend to use it a lot. You'll get an exact solution, of course, in p steps, but you'll get a very, very close to exact solution in 5 or 6 steps. Maybe not 5 or 6, maybe 10. Depends on the dimension of your problem, obviously. A lot of research goes into figuring out what 5 or 10 actually is, rather than my just off-the-cuff telling you that 5 or 10 will work here. But it's a heck of a lot less than p, and you get a much improved runtime by doing this. And I was really excited to see Joel Tropp's talk the other day, because now I'm going to run home and try all of his ideas for, instead of doing Pulov subspace methods for a problem like this, to do his ideas based on randomization for getting an approximate solution. Any approximate solution will work as long as you can check, and it's really simple to check whether you've improved the observed data objective function at the intermediate stage of the EM. Okay? And what's even better is, what's the bottleneck here? Well, the bottleneck here is to take this p-dimensional vector D and just beat on it a few times with this p by p matrix A. Well, I can parallelize that really easily. So we're actually running this on a supercomputer at Texas for that 112 million patient record data set called Ranger, which is a great name. And there's physicists simulating the early universe and most of the computer, and we have a tiny little epsilon ball corner of this computer devoted to solving my small stats problem. So, of course, there's lots of algorithms, and I haven't had time to give you a full kind of rundown of comparisons for these algorithms. But all these alternative approaches for solving these kinds of problems all suffer from deficiencies in a variety of ways. Not to say ours is perfect. Probably the two that you'll hear about most are coordinate descent and variational methods. Variational methods are super fast and pretty easy to implement for some cases and a lot harder for others. The problem is, of course, they're never exact. Mike Titrington has an interesting paper a few years ago in JASA, I think, showing that they can be inconsistent under some pretty simple cases, which is worrying, of course. And of course, coordinate descent, well, okay, yes, it can get stuck. So can ours in local modes. Because we're getting block updates, it's less likely to get stuck. This is the part that I don't like about coordinate descent, is that you're never going to parallelize something that's intrinsically coordinate by coordinate. Whereas we get a block update, it's based on matrix vector multiplication, you can parallelize that embarrassingly easily. In 1 minute, I'll give a rundown on how you would do MCMC in this class. For those of you that have implemented these models, you might imagine that doing an update for a variance term whose prior is an infinite convolution of exponentials is kind of tricky. Turns out that it's not so hard, and we can do it. And we just exploit this kind of interesting fact having to do with the cumulant transform of a z distribution. That there's this sort of bizarre duality between a precision representation for this latent variable and a variance representation for this latent variable. This is, again, a weird math fact that my collaborator sort of unearthed here. But we just are able to exploit this fact within this class of Poya densities to do nice closed form updates. And what does it get you? It gets you this class of what we call Poya gamma distributions. Technically, you have to draw an infinite number of them. I'm a statistician, so I'll approximate infinity by 10, and that'll be my MCMC. Okay. I think That's all I've got. This algorithm that I've showed you really does work, and we've tried it for a whole bunch of these with arbitrary combinations of the left and the right. So pick your model, pick your penalty, and go to town. Thanks very much.
Yes.
Quick question. You mentioned that you get stuck in local minimum or maximum. Can you describe what type of settings?
Can I didn't quite hit the second.
Settings, do you notice the algorithm does get stuck?
Well, it's like any of these algorithms. It'll get stuck when you have extreme collinearity in the design matrix. And coordinate descent does the same thing. I guess the point I was trying to raise is that anytime you go outside the realm of nice convex optimization problems, you really have to worry about getting stuck in local modes. We do too, but because we're not updating coordinate by coordinate, we're getting a whole block update. We're just a lot less likely to get stuck. I don't have any theory that says that, but you know, the parallel experience would be consider the original Gibbs sampler that updates coordinate by coordinate in a big MCMC versus a block Gibbs sampler, and in most cases the big block Gibbs sampler is going to get you faster convergence than the coordinate by coordinate one.
Yes.
So how does it scale computationally in NP? Like, if you have a million predictors
How many cores will you give me? You know, it scales, so formally speaking.
like also in terms of the rate of conversion.
Okay, so there's no theory in this that I have that says this, but how many EM steps do you need to take? Well, that depends on the collinearity of the design matrix and how quickly you can move around the space. How quickly can you solve an individual EM step? That's, let's see, n plus p, basically auxiliary computations, plus the matrix solve. Okay, so that would be p cubed, but if you don't have to solve it exactly, we're talking something like k times p squared, where k is some factor, you know, am I going to run the conjugate gradient algorithm 5 or 6 times? But that's parallelizable. So give me 1,000 cores and 1,000 dimensional problems, and I'm something much more like p.
If not, let's thank our speakers.